today is kind of finish up this whole long story that I've been telling you about canonical quantization, about the bosonic quantization, bosonic oscillators, and fermionic quantization, and the fermionic oscillator. So I want to kind of finish that story, and then also kind of go back, and there's one part of it that was kind of where there's a lot of detail earlier in the book, which I've skipped, which is this kind of this business about complex structures. I want to kind of go over that story and kind of go back and pick that up and explain what that's about. And then once we've done that, we'll kind of move on to the next part of what I want to do, which is in some sense can be thought of when you can put the bosonic and fermionic stuff together, take a tensor product of the two of them, and then you can actually get interesting operators that mix the bosonic stuff and the fermionic stuff, and you get simple examples of what people call supersymmetry. So I'll start on that. Okay. So that's the plan for today. So let me start with the kind of summary of what we've done so far. So there's actually a table in I guess I made a whole chapter out of it. There's kind of a table in chapter 32, which is kind of tries to summarize all this. So let me just kind of quickly say some things about that table. But the idea is this: that you've got a completely parallel structure between the bosonic canonical quantization and the fermionic. And in both cases, you're starting out with a vector space R2D, and so what you should think of it as really as the dual phase space is the dual to the phase space, and it is R2D. And you can think of it the same way. It's the same thing over here, and sometimes I call it. But there's some underlying even dimensional real vector space, which is where your degrees of freedom are. So you think of this as being a system of d degrees of freedom. Here you've got dp's and dq's. Here you've got 2D fermionic variables, but they can be so this is a little bit of this is not the most general case that you can actually make the fermionic story work when this is odd dimensional, but then you have to kind of can't do a lot of the things that you can do here. The kind of analogs of Bargmann and Fock can't be done. So this is kind of a special case of an even dimensional number of fermionic variables. And then on this side, you have an antisymmetric bilinear form, which I'll call omega. And here you have a symmetric often written just with parentheses. You have an antisymmetric bilinear form, and both non-degenerate. And then here you've got you can use this on linear things. You could extend it by the like a Leibniz rule to higher to any polynomials, and you get a plus one bracket. So on polynomials, the plus one bracket is determined by what happens on the linear things, or by this antisymmetric form. And it's the same thing here. You've got also you could extend this to these kind of anti-commuting polynomials using this way. And then here you've got a Lie algebra of polys of degree less than equal to 2, and it's the same thing here, and it's the anyway, it's the same thing here. And the Lie algebra here, this is the Lie algebra of SO 3D. And here it's the Lie algebra of SP2D. And you can think of so this is the group that so you could think of this as being preserved. That your kind of almost your definition of what this group is it's the group that preserves this. So this guy gives you an SO2D. That's the group of linear transformations of R2D which preserve this form, and this guy gives you a SP2DR. And then the other thing is to say, yeah, and so the anyway, so okay, so wait, sorry, I should say, so it's the quadratic of the, sorry, so anyway, so you get a Lie algebra of polys of degree less than or equal to 2, and same thing here, and then the degree 2 ones are give you this, but you also have you also have things that are degree 0 and degree 1, and here it's actually becomes it's actually a Lie super. You have to say super algebra if you want polys. The algebra polynomial is less than 2, and the ones that anyway degree 2 is Lie SP. Okay. So the quadratic polynomials in Q and P, with a Poisson bracket, give you the Lie algebra of SP2DR, and the quadratic things in the generators psi j and psi k here give you the algebra of the orthogonal group. And then when you quantize these polynomials, you get an algebra of operators, and this side is what I called the vial of 2D. See, it's the algebra of all the P and Q generated by the P and Q operators. Algebra of operators. Here you get the Clifford algebra. C. Anyway, and it's the same thing here. Then the quadratic. So degree 2 to polys in P, J, Q, K. Oh, let me not write this down. Let me just say a few of these things, because otherwise this is going to get too much of a mess. So then what happens is that when you quantize, these polynomials become operators, and the degree 2 combination, the degree 1 stuff over here becomes the degree 0 and 1 stuff becomes the Heisenberg algebra. Over here it becomes something which doesn't really have a name. It's a Lie super algebra, but it doesn't really have a real name. On this case, and then the degree 2 stuff gives you a representation of the Lie algebra of the symplectic group. And here you get a representation, and that's the metaplectic representation. So I should say that over here you get. Right. And here you get the spinor representation. So the degree 2 things in the Clifford algebra generators act on the spinor representation. That's your kind of fermionic space of states, and the degree 2 things here act on this metaplectic representation. So which are there many ways of thinking of it? You can think of it as L2 functions on RD, either in functions of Q or functions of P, or you can think of it in the Bargmann-Fock way. It's kind of polynomials on CD. Okay, and then a lot of the yeah.
So I just want to make sure that so can we say the common point of the group is that, well, the algebra is that you form an algebra generated by one and some vectors in the algebra. You just apply the algebra brackets, so you know how things exchange, and then form the wild group of triple groups.
Well, no, I mean,
wild algebra and triple algebra.
well, so these, the Weyl algebra and the Clifford algebra are not so related to the Lie algebra. So this is an infinite dimensional algebra of kind of all powers of P and Q. Okay, so it's got all arbitrary ones, and this Clifford algebra has got all of the things you can make by putting together gamma matrices. Okay, so these are kind of big algebras, but sitting inside these is the so inside here you've got the degree 0, 0, 1, and 2 things inside here, and it's the same thing in here. Inside here you've got the things that you can make out of degree 0, 1, and 2 in the gamma matrices. So these algebras are not I mean, these algebras are not Lie. The Lie algebras that you've got are the Lie algebra here and the Lie algebra. So the Lie algebra. So this is all powers of P and Q operators. Okay, so you can have arbitrarily high powers you want. It's a huge algebra. Sitting inside here, there's kind of a finite dimensional subpiece, which is the identity operator, the linear combinations of the P and Q operators, and that gives you the Heisenberg representation of the Heisenberg algebra, and then the degree 2 things, and that gives you the symplectic Lie algebra. And then sitting inside here are kind of everything you can make out by multiplying gamma matrices, and that's kind of all 2 to the d by 2 to the, that's all 2 to the d by 2 to the t matrices. Now inside all 2 to the d by 2 to the d matrices, there's there's the representation of the orthogonal group on the spinors. So those are just and these are the things you get from just the gamma J, gamma K. Okay, so are in here. So it's a bit confusing. I mean, these are kind of big algebras that you created, but these kind of Lie algebras of symmetries are kind of just a special subalgebra. Does that help? Okay. And so just to say again in words, so there's kind of the Stoneman-Neumann theorem, which says that there's really only one, up to unitary equivalence, there's really only one irreducible representation of this Lie group. And the same thing is true here, that there's really kind of there's really only kind of one irreducible representation of here it's the spinors. And here, and both of these representations, you have to watch out that they're not that they're actually a representation of the you have it. So these are only projective representations of the SP group. That they're actually they're true representations of double cover. It's a double cover. SP. Sorry. And here you have spin of 2D. So I mean, the most kind of subtle piece of this whole story is the fact that you're these Lie algebras that you're getting representations of by using the gamma matrices or by using the P and Q operators. If you try and exponentiate those operators, you find a weird sign problem that as you go around as you go around a circle in the SP group or a circle in the SO group, you pick up a minus sign. And so you need actually, so what you're actually getting are not representations only up to a sign of SO or of SP. So what you're really getting is a representation of the double cover. And in the case of the SO, the fact that that this SO group has a double covering group, I kind of already mentioned it. And this is what you've done is you've actually constructed that group as by it's the thing you get by exponentiating these order 2 things in the Clifford algebra. So this becomes a group of matrices. It's the group of matrices you get by exponentiating linear combinations of these matrices. This one is even more subtle because you have to kind of understand what it means to exponentiate, pairs of Q and P operators, and that's a bit harder. I mean, anyway, that's kind of an infinite dimensional problem, which is kind of a problem which is harder just to say to really nail down. Whereas here, it's you're just exponentiating matrices, but it's the same problem. But this extra kind of sign problem, it's a problem that kind of reoccurs. It occurs in an interesting way on both sides. And in both places, it's kind of subtle. Anyway, and then the okay. So let me. So maybe that's all I want to say about this. So then there's an extra piece of the story which I haven't really. So this part of the story doesn't really involve the the Bargmann-Fock story. I mean, this kind of part of the story you could say without talking about annihilation creation operators and without the whole and without thinking about the Bargmann-Fock version of the representation. You could just think about the L2 over here, or you could just think about just matrices over here. But the whole story about how to kind of think about this piece of it, in terms of harmonic oscillators and in terms of not just functions of P and Q, but kind of holomorphic functions of Z. And in this case, how to think about it in terms of, again, in terms of something that's going to give you a fermionic oscillator, a fermionic analog of the harmonic oscillator. That you have to introduce an extra piece of structure. Okay? So, and that I haven't really, is something I didn't really emphasize. I hadn't really explained so far this course. I mean, I just kind of picked one extra way of doing that. And what I want to do now is kind of go back and explain, what that extra piece of structure is and what the and how to get that and to see that there are other possible choices. Okay, so I'll stop with this analogy here, but the next thing that I'm going to tell you, in some sense, gives you extra entries here. It's going to kind of, I'm now going to introduce a new piece of structure in a way which you can then extend this to the whole story of the bosonic oscillator and Bargmann-Fock, and you can extend this to the whole story of the fermionic oscillator. That's the plan. Okay, so let's back up. So now, this is a story about what's called what are called complex structures. Okay. And so maybe it's a good idea. So the thing to recall that, what did I do? So if I started with the Q and P operators, and I realized that if I wanted to develop this kind of formalism of annihilation creation operators and really do the harmonic oscillator in a nice way, that the thing to do was to kind of to create some non-self-adjoint combinations of the Q's and P's operators by allowing myself to take not just real linear combinations but complex linear combinations. And remember what I did was I think I defined it what so ZJ. I defined Zj be 1 over square root of 2 Qj minus Bj, and then Z bar so what I was doing here, is I allowed myself to throw in these eyes and to take complex linear combinations of things, and then when under quantization, this guy then gave me this one gave me the AJ dagger operators, and this one gave me the AJ operators. And so quantization, you got not self-adjoint operators, but operators that were adjoints of each other. Okay, but the trick was but there's something kind of funny about this. I mean, besides the fact that wait a minute, why? I had this nice real Lie algebra. Why am I complexifying it and doing stuff? But the other thing is that I've picked a very special complex linear combination of these guys, and so it turns out that everything that I'm doing, the whole structure that I'm creating of annihilation creation operators satisfying these kind of standard relations and the whole kind of harmonic oscillator picture and the whole Bargmann-Fock picture, that you could actually do that in more generality. That there are many other linear combinations of the Q's and P's that you could pick, which would make that still work. So what I want to do is I want to kind of explain what's the right kind of piece of mathematical structure that you want to choose. Here you made a specific choice of it, but that there's more general possibilities, and what's the most general possibility that you can, of a choice of structure you can make that's going to make this whole formalism still work. Okay, and this is going to be what a complex structure is. So let me say, so the abstract point of view is we're starting. So you start with you're starting with it with an even dimensional vector space, and in the case of so in the Bosonic case, that's going to be think of it as the dual of the phase space. But then what you're doing is then you consider you consider the complexification. So what this means is you take this vector space where you only really know how to multiply things by how to take kind of real linear combinations of things and allow yourself to take complex linear combinations of things. That's all that means. Okay, and then now what you want to do is you don't just you want to find some way of breaking this up. So you want something that gives R2D C is equal to C to the D plus C to the D. Okay. So you want some extra piece of structure that where it's going to, where these are going to be your Zj, and these are going to be your Z bar J. So you want what you're doing here is you're introducing, you're not just looking at complex linear combinations of real things. You're also, you're going to need some very specific piece of structure which is going to tell you, what it's going to break this up. So this is really the C to the 2D. You now created a 2D dimensional complex vector space, but you want something. You need something else. You need some way of taking this complex 2D dimensional vector space and deciding that and breaking it up into 2D dimensional pieces like this, and the kind of subsets the holomorphic and anti-holomorphic stuff. So this is one way of doing it. Here you're just saying that I'm going to take, things that are complex linear combinations of these guys are going to be the Z are going to be live in here, and things that are complex linear combinations of these guys are going to live in here. But I want to do this more generally. So what you do is you need an operator, a linear operator, later. J that takes R to the 2D, R to the 2D. Okay. And then and such that J squared is equal to minus the identity. So the extra piece of information that we're gonna need is and this is what's called this is what I call a complex structure. So when I say that I've chosen a complex structure on R2D, that means I picked a linear operator that that takes this to this and whose square is minus the identity operator. And you should think of this as being one way of thinking about what I've done is that I've said, look, I want to one thing I want to be able to do is I want to identify my R2D with this space, with this CD. I want to think of this CD as being my original R2D with a certain choice of what it means to multiply by I. And if I want to figure out what it means to multiply by I, what it means to multiply by I is to have some kind of linear transformation of some kind of real linear transformation of the vector space such that I squared is -1, so I squared X is like that. So this J in some sense it's a thing whose job it is to tell me what I is if I try and identify this R2D with this CD. And another way of saying that is that it's so this has if J squared is -1, it's going to have its eigenvalues are going to be so this has eigenvalues lambda, so lambda squared is equal to -1. If you start saying, okay, now if I want to diagonalize this guy, if I want to find the eigenspaces, not diagonalize, but if I want to find the eigenspaces of this guy, I want to find what are the eigenvalues. Well, the eigenvalues, okay. Oh, so first I have to, one thing is, I have to realize that if I know what J is on this way, on this I can extend it by complex linearity so that I also have an operator, on the complex. I mean, so just if I have such an operator, once I throw in complex coefficients, I still that operator still works on this space. But now it's going to have certain eigenvalues, and the eigenvalues are going to satisfy this. And so so the eigenvalues then have to be lambda is plus or minus I. Okay. And so then what you find, so then what you say is that the eigenspaces, so V plus is the plus I eigenspace, and V minus is the minus I eigenspace. And so what I've got now is this. Take this. So really, so what I really got is I've really got V cross C is equal to V plus V minus. So this is the and these are so this is the plus I eigenspace, this is the negative I eigenspace. And then if you're going to take a and then if you conjugate here, conjugation takes things that have eigenvalue plus I to things with eigenvalue minus I. So you've got this, you've broken the space up into these two pieces, which are then related by conjugation. And this is going to be your kind of abstract analog of, this is going to be spanned by the z's, this is going to be spanned by the z bars. Okay. Okay, and then so the special case we had, so that we started with was that V is equal to the, you know, the dual phase space, and you've got and then J0, and this has a basis. Well, this is a basis QJ PJ, and then the J is the operator that takes. So if you take J is equal to J is equal to a special thing case of J0, and you take QJ to be QJ to be on QJ, it gives you PJ, and acting on PJ, it gives you minus QJ. Is that right? Yeah. And so you can see, so this is something that you can see that J0 squared is equal to minus 1. It acts, you know, if you do this twice, you're always going to get minus the identity operator, and you could compute what it does on ZJ. And if you went back to the ZJ that I wrote down, you'll see that the ZJ, and compute what this does on ZJ, you'll find that it gives you I times ZJ. So the ZJs are the basis elements in the plus I eigenspace of J0. Okay, so anyway, so this is the most general story. Let's see. I want to. Okay. Yeah, anyway, so this is the most general gadget that's going to do what we want. But there's a specific example of it is this guy. But the point is that there are other. I mean, there are other operators I could have chosen that also square to minus 1. That would also work. Okay, let's see.
Is this operator Arizona matrix one just like the symplectic two-form?
Yeah, no. So wait a minute. So the next thing I'm going to get is the relation. So right now these operators are just they're just linear operators on this 2D dimensional vector space. Okay, maybe I should say this now. Yeah, let me just think. I guess I've said the other things I want to say, which is that this. Yeah. So okay. So now I'll get to what you're asking about, I think, which is this. Okay. So right now, let me see this. Okay. So in general, so J. Okay. So if J is going to square to be minus 1 and it has eigenvalues plus or minus I, it's gonna be in general J. It's going to be some linear operator on 2D real space. So it's 2D R. I mean, because of this, it has to be invertible. So in general, you can imagine that it's a that if you just pick if you pick such a thing, it's going to be it has to lie in this space. But then you can then if you pick such a thing, what it does is it picks out a so choosing J picks out GL C to D C sub QDR. Okay. which is that you can think of, you can ask, once you picked a J, you can ask for so it's that all G. And so if you've got some group elements in here, and then here these are going to be the G such that G J is equal to JG. So the things, the G's which are once you found such a J, big J, then you can ask, okay, what about, it's an example of an invertible linear transformation. But I can now ask, what are the other invertible real linear transformations that commute with it? And then if those things, if you start interpreting this as playing the role of an I and identifying R2D with CD, then if the G's that commute with it are actually going to be the things that you can interpret as being the D by D complex linear transformations on, let's say on V plus. Okay, so anyway, this choosing such a J, one of the nice things it does, one of the things it does in general is picks out such a thing. But now, in the Bosonic, what we're going to do though is in the Bosonic case, we want to choose J, not just that it satisfies some extra condition. You want to choose J to be symplectic. And in the fermionic case, we're going to choose J to be in the orthogonal. You might also want to talk about J's which also reverse the orientation and use your orthogonal group instead. But this is going to be the story. Is that the before you start thinking about bosonic or fermionic, and before you start thinking, so this means that preserves. So this means that omega of J V J W is omega of V W, and this means that J. Okay, so you can, when you're going to do bosonic quantization, you want to focus on what's going to be needed in order to make the whole thing work is to have complex structures that satisfy this, so that they that if you that their action preserves the symplectic form, the antisymmetric form. And if you want to do fermionic quantization, you're going to need J's that it preserves the symmetric bilinear form. Okay.
How do we show that from just from the commutation or anti-commutation of the creation and annihilation operator to the fact that this linear operator has to be either symplectic or the.
Well, I haven't shown that yet, but I'm just saying that that's where this is going. So the point is that if you look at the whole story of how we're so what's going to happen in the bosonic case is when you quantize the Poisson bracket is going to become this commutator, and you want a certain relation satisfied by the Poisson bracket to become this kind of standard end commutation relation. Okay, you're going to have a z bar. Just in one case is I, and this is then going to give you your a dagger is 1, right? Okay, so in the Bosonic case, you've got what really determines the Poisson bracket is this guy, and the Poisson bracket is what determines your commutation relations, right? And so you want anyway, so in order to make everything work, you need, I'm just saying that, you know, you need J's that, anyway, your J has to preserve it has to preserve this guy and has to then preserve the Poisson bracket. So, I mean, I haven't yet developed it. I haven't actually done all this, but you can kind of see what's going to happen. That since this is the guy which determines the whole structure, which is going to give you your commutation relation, that give you this, then this guy better do something like this. And then the same thing in the bosonic case, that, you know, these guys, the analog of this is going to be given by this guy just by the inner product of that kind of bilinear form, and this guy better preserve this guy in order to make the whole formalism of fermionic oscillators work. So I haven't, you know, done it all yet, but you can kind of see that you're going to need some condition like that. Okay, now let me now kind of say something that there's and all of this stuff. Well, anyway, so this whole kind of formalism of developing, starting from this definition of what a J is, and then developing the formalism of annihilation creation operators and showing that you know it works in this more general case. It actually is written out in a couple chapters of this book, kind of in way too gory detail. But what I realized is there's some things that are really kind of not explained very well in there about how this is all working. So the next thing I want to tell you is something. Anyway, so if you want more details about that, they're there. And anyway, there's some various technicalities you have to check as you go along. You have to check that this is all going to work out the way you want it to work out. But that's the general. But there's one thing which I should have kind of explained in the book, which I didn't. Let me tell you this next thing. So the right picture of the relation of all these things to have in mind is really kind of this. So this is a picture. So let's say you think about all invertible linear transformation. It's at some big space, but it's just 2 by 2D invertible matrices. But anyway, so now sitting inside here, once you pick if you pick a J, you manage to find an element, something inside here whose square is -1. Then you end up with the space right this way, which is going to be GL of DC, which is isomorphic to D by D complex matrices, and this is given by a choice of J. Okay, that it picks this out, and it very explicitly. It's anyway. The point, the claim is that you can thinking of this J as acting as an I. You can consistently look at D by D complex matrices with this your notion of I, and these now sit inside here. Okay. And now, but now the more fun part of the story is that you can think of, you know, within these guys, you can think of another thing, which is you can ask for what about the SP of 2D R. And so this is given by a choice of omega. So if I pick an antisymmetric non-degenerate bilinear form, omega, that picks out a subgroup here, the symplectic subgroup, SP2R, right? But now even better, the other thing to realize is you can pick it. There's another thing you can do, which is this, which is you can pick just a symmetric bilinear form, And that gives you an SOD, SO2D. Okay, subgroup. Okay. So anyway, in the now the interesting thing is the way I've drawn this kind of implies that there's an interesting subgroup here, which is both preserves one of these, and preserves J, and this is going to turn out to be a subgroup, a unitary group. So transformations inside here which commute with J, which preserve omega, and which preserve this guy, satisfy these three conditions, are actually going to be unitary transformations, unitary d by d transformations. And
so you mean any two sets of those three do not have a independent intersection?
Yeah, exactly. So this is what I want to explain next. I mean, the amazing part of the story is that you only need, if you satisfy two of these things, if you preserve any two of these guys, you preserve the third. Okay, and so that's the kind of beauty of this whole subject. And one way to see this is that you can define a Hermitian form by taking omega is equal to plus I okay. So the idea is that I can okay. So this is a Hermitian form, and what this guy is, remember, is that so he's defined on on R2D cross C is equal to, well, CD plus CD. So this is going to be, or this is going to be positive, positive here. So anyway, so if you use these, so in this picture, you may be given this kind of symmetric bilinear form on R2D. You can extend it by complex linearity to one on here, and then the same thing here. If you're given an antisymmetric form on R2D, again you extend it by complex linearity to all of this guy. And now if you restrict attention, if you restrict these guys just to the subspace on where the J is equal to I, then what it turns out that you can actually get you actually get a Hermitian form. You get a Hermitian form. So on this guy. I mean, actually, what you get is what's called on the whole thing. You get a pseudo Hermitian form. You get something which is positive here and negative here, but it has the Hermitian property. But it's a Hermitian one here. And so the reason all of this works is because given. Okay, so the kind of the 2 out of 3 of these things. Well, let me say it in this way: is that if you're given a J, and if you're given a J, and you're given this guy, so you're given a J which lies in here, it lies in here and in here. Then what you can do, you can define this guy, but you only know this guy, so you have to figure out what this guy is going to be. You can have you can define. So if you just know this guy, you can define this guy by omega of VW is this guy and VJW. Okay. Or if you just know this guy and you want to know what this guy is going to be, you can define this guy Here. B. Oh, sorry. J. And then anyway, it's a nice. You can then figure out you can figure out that this is consistent. So for instance, if this guy is a symmetric bilinear form, and you apply him to this guy, what you want to show that this guy is actually a what you find is that this guy is equal to minus So you want to show that if this guy is symmetric, you want to show that this gives you an anti-symmetric form this way, and to show that, I think I won't take the time to work out the argument, but you basically just use the fact that the you use v w equal to j v a w, and j squared is minus 1. So if you if you multiply both of these by j and use the fact that this is minus 1, you're going to get that. You get the anti-symmetry property. So this j squared is equal to minus 1, and this invariance property allows you to kind of, if you're sitting in here and you've got j and you've got this guy, then you've also got this guy. And similarly, if you're sitting in here and you've got this guy and this guy, you've got that guy. And then in either case, once you've got both of these guys, you can say this, and this thing, if you look at it, this has all the right properties to be a Hermitian form. Remember, Hermitian form has got its real part is symmetric, and its imaginary part is anti-symmetric. So this has all the right properties to be a Hermitian form. And then you can say that so then things which preserve both this and this, so they preserve a Hermitian form. I mean, that preserving a non-degenerate Hermitian form is what it means to be unitary. And so the things which lie in both either of these are unitary things. Okay. Anyway, so that's the kind of abstract nonsense. Yeah, and let me maybe. So this is called kind of at the level of groups, and I didn't really say some of this in the book, even though I should have. Once you at the level of the algebras, what's going to happen is that you're going to have the things that are going to things that are going to be in here are going to be skew adjoint operators, and these are going to correspond. Well, these are going to, so this is going to, what's going to happen when you quantize is here you're going to get kind of arbitrary quadratic things in A and A dagger. Here you're also going to get arbitrary quadratic things in A and A dagger. But in here you're going to get the subgroup of things that have one A quadratic things that they have an equal number of A's and A daggers. Okay, that's going to be, so at the Lie algebra level, that's what's going to distinguish these guys. At the Lie algebra level, you're going to have, you're going to have things like A squared and A dagger squareds in here and here or here, but the things like, it's the things that are some AA dagger kind of terms are going to be the things that are in here. And that's what I kind of, you've seen a lot of that. I think if you worked out these problems and if you worked out the, it's also worked out in detail in the book, is kind of the Lie algebra version of that story. But anyway, this is the abstract. I guess there's one subtlety to watch out for. Let me just say let me just say it is that you have to. Okay, so well, I mean for this all to work out, and in order to get a kind of a standard set of, so in order to get a set of annihilation creation operators that you can kind of think of as being like harmonic oscillator ones, you have to have some kind of positivity condition. You don't want these you want these annihilation operators to have some lowest energy level where they're going to stop. You don't want states to go all the way down. You want them to states just to go in one direction. And so this corresponds to some kind of positivity condition. On this guy, it's just the standard positivity condition. It's just the you want a positive inner product here. On this guy, you have to watch out that that there's an extra condition you need on your omegas, on the things in here, that you can't take any antisymmetric bilinear form. You have to take an antisymmetric bilinear form that satisfies this condition that this guy, that when you create this guy this way and put it together in here, you're going to have a positive Hermitian form. Okay, so there's an extra positivity condition on the things in here in order for this to work out. Anyway, that's the abstract nonsense. Now let me tell you quickly, just quickly say one quick example, and then we'll move on. Oops. So just a quick example. If D is equal to 1, well then GL of D C is C star. SO of QD is just equal to U1. So in this picture, I mean, there is no, everything in SO is actually in UD. There is no extra P, there are no extra P's. But then you have SP QD R is SL2R. Oh, sorry, SL2R. And remember, and so you've got a U1, which is, inside of all these. It's equal to that. Okay. So there's a U1 inside of all of those. And it turns out the inequivalent, the possible J's are parametrized by, so this is a little bit of a longer story, which is worked out in the book, but I want to just say this quickly. So in some sense, you want to look at J's that are in here. Sorry, I should have said, this is just, well, yeah, okay, that's right, yeah. So the J's that are in here, what you're interested in is the J's that are in here kind of modulo the ones that are in here, because the things in here that just generate kind of unitary transformations that don't change the distinction between homomorphic and anti-homomorphic. These guys do. So they're parametrized by, in some sense, SL2R modulo, where you're gonna, where the ones that are related by U1 are in some sense giving you the same, they're giving you the same breakup of the vector space into holomorphic and anti-holomorphic. And so, and this space is actually the upper half plane. You can identify this with the upper half plane in C. And this is, sorry, this is what I'm kind of not telling you how to do in detail. But if you, anyway, you can identify this with the upper half plane, and then so your J's are given by anything in the upper half plane, and the standard one is I is equal to J0. So the standard, there's a standard one, but it could be anything, and you can generalize the whole story to so you can do the same. So you can do a harmonic oscillator later, for any j, but it's for any tau, which is an element of C with the imaginary part of tau greater than or equal to 0, or greater than 0, better say. Okay. Because so any kind of j in this upper half plane will work, and you can actually you can do it. The fact that you have it's in the upper half plane is the positivity condition that it's going to give you a positive Hermitian form. But these guys, for different choices of tau other than the standard one, are called squeezed states. So the whole story about harmonic oscillators has this generalization to a story parameterized by points in the upper half plane, and you get different behavior as you move tau around, and in particular, the lowest energy state depends upon your choice of j, because this is going to be the thing that anyway, you're going to get annihilation creation operators that depend upon your choice of j. They depend upon tau. This is going to be the thing annihilated by the annihilation operators. And if you write it back in the Schrodinger picture, this is going to be proportional to e to the I over 2 times tau over tau squared q squared. Okay. So if tau is I, then this just becomes e to the minus 1/2 q squared, and it's the standard, nice Gaussian lowest energy state of your oscillator. But you can see that. But you can also, but these squeeze states are going to be states of this form where tau is not necessarily I, but tau is something else. It can have both an imaginary and real part, and then you're going to get some more interesting kind of ground state, and you're going to get all these oscillator states, which you get by applying the kind of tau version of the creation operators to this guy. Okay. So anyways, there's a section in the book at the end. I forget what it was. Anyway, I forget, section 26.5, I think. Anyway, where I actually work this kind of case out in detail if you want to play with it. But you also can see this in the if you look at the people who are doing kind of quantum optics, you'll find that they're thinking about kind of photon. They're thinking about how to create photon states, which are quanta of oscillators corresponding to these different kinds of j's, which are not the standard one. That's what squeeze states are. Okay, so I think better, let me see, is that? Yeah, okay, I think that's all I wanted to say about complex structures and fermionic quantization. So are there any questions about any of this stuff right now so now I'll kind of go on to a different topic, but let me give you a chance to stop here if anything's. And again, I haven't worked out the details of the whole formalism of what annihilation creation operators look like for arbitrary j's. That actually is worked out in the book, and in retrospect, anyway, I was kind of painfully working out exactly how all that works and how it shows that it has the right properties. But besides these cases of squeeze states, to be honest, there's not that many applications of that whole formalism, so I don't want to spend more time on it. You can do it. Okay.
Kind of just stupid question, I guess. But so you have tau over modulus tau in the exponent.
Yeah.
So that's the argument of tau.
So sorry.
Sorry.
I think this is this. Sorry. Sorry.
Oh, okay.
Okay. Yeah. Sorry. Yeah. So this is real, and the yeah. So it's actually 1 over the conjugate of tau, but yeah. Okay. Any questions? Okay, so let's go on to start on something completely different.
Actually, one more question about the squeeze state. So do we still use the same analogy. Wait, so first of all, does the squeeze state still satisfy the ladder condition for the eigenvalues?
Yeah, yeah. So it satisfies the No, I've forgotten. Yeah, yeah. I mean, you still have a number operator. There's still a number, and you can work this out. So yeah, you can work out what the formulas are for 8. Yeah, and yeah, and so you're going to have a Hamiltonian, which is going to be basically H 1/2 A tau A dagger tau plus A dagger tau A tau. Yeah, and so yeah, and anyway, you can work out what these guys are in terms of the standard ones. So these guys are going to be just linear combinations of your standard A and A dagger with certain coefficients, which are functions of tau. Okay, and so you can work out what they are, and so you get this is just some kind of anyway. Yeah, so this is some kind of complicated functions times the usual A and A daggers, and from that you can explicitly calculate the spectrum and see what it looks like. But there is an analog of that. You still have number operators with the right properties and stuff. Anything else? And I think yeah, there is a lot more detail in that section about it, how that works. Okay, so let me just start. I guess I won't get very far with this today. We'll do more on next time. But let me just think what So the idea now is to put is to consider. What we want to do is we want to consider systems where let's take the well. I think I also gave this a name. So F is the for Fock space, which I'll explain more later. Is the harmonic oscillator is the bosonic. Like Bargmann-Fock space. And so this is, you can identify with the polys on CD. And this is D. And then I've got the antisymmetric version of it, which I call this, which is the fermionic. So this you can think of it as being the symmetric algebra on CD, and this is the fermionic. So it's also, and this one is the antisymmetric tensor powers in CD. And now, but what you can do is you can put these together. You can consider H the. Let's put these together. Let's take their tensor product. Okay. So so far I've just talked about here just about the harmonic oscillator, or here just about the fermionic oscillator, and the operator. There are operators that act out here, operators act out here. What I can do is I can take these together, and then there's going to be interesting operators that mix these two things. Okay. And so let me maybe the quickest way to see this is just to take. Oh, okay. So now let's just take our Hamiltonian to be the just to be the sum A is equal to 1 to D. Take the Hamiltonian just to be the standard Hamiltonian you would have for thinking of these as decoupled things. This is just so it's just let's see, the bosonic number operator for the jth quant in the j for the jth one, and the fermionic number operator, or so and then times like whatever the quanta h bar. So putting some constants in, so you can scale this, and so this is so n the j is the A, B, the jth one, a dagger, A, and F, J, F. So I'm just, so now I can't get away with just using A's. I have to tell you whether they're bosonic or fermionic annihilation creation operators, but I've got both. And I've got, and I can create a Hamiltonian, which is just what you would, what you would expect if you just couple these, put these things together. You've got an energy that depends upon your bosonic quantum number and your fermionic quantum number. And and I've chosen to put them together in a specific way so that they each have this, they have the same constant in front of them. So I'm assigning the same energy to a fermionic quanta or a bosonic quanta. Okay, so now the interesting, so what happens now is you have H, so this has eigenvectors. We'll call it N, B, and F, with H and B and F is equal to N and B plus, just realize there's a kind of obvious typo here. Anyway, and B plus and F. Okay. Oh, sorry, and there should be an H bar omega here, which I'll now probably I'll start setting equal to 1 right now just to avoid that. So anyway, so the energy eigenvalues are just going to be these integral things. And then what you have is that the okay, now notice that NF, so NB is going to be 0, 1, up to infinity, and NF is going to be, oh sorry, I think right now I better take, let's take J is equal to 1 for simplicity, and B is equal to, and then I've got, this is going to be 0 or 1. Okay. Okay, and now let's actually draw a picture of the energy eigenstates. So what you're going to have at so down at energy 0, you're going to have 0, 0. It's going to be the ground state, because we're, no fermionic quantum and no bosonic quantum. And then up at H bar omega, you're going to have things. Oh, and also notice the fun thing here is that this business about the business that you had to worry about the halves before, that in the bosonic case you were picking up a half, and in the fermionic case you're losing it. Well, they cancel here, so there are no halves. Okay, then and here you've got 1, 1, 0, and 0, 1. So you've either got a bosonic thing and no fermionic thing, or no bosonic thing and a fermionic thing, and then at 2 H bar omega you've got, again, let's see, 2, 0, 0, and 1, 1, and at 3 H bar omega you've got 3, 0, and 2, 1. So what you find is that the spectrum of this coupled oscillator, this coupled thing, is given by, it's again quantized in these usual units, but at each stage you actually have 2 possibilities. Okay, and these are eigenvectors of the Hamiltonian. But now this is where something interesting happens. Is that what you can do is you can define. Let me define it down here. You can start playing with operators that take you from that interchange fermionic and bosonic that go from one to the other. And in particular, you can define Q plus is AB AF dagger, and Q minus is the other one, AB dagger. Or AF. And then what you find then is that these guys then Q plus takes you here, and Q minus takes you here. So these operators now take you back and forth between these things. And what you find is you find these relations. You find Q plus squared is equal to 0. That this is a nilpotent operator. If you do this twice, if you try to keep going this way, you're going to get 0. And Q minus squared is equal to 0. So this is just from the properties of the annihilation creation operators. But what you also find though is that Q, if you take Q plus Q minus and square it, you're going to get the Hamiltonian. Okay. So another way. So what happens? So this is kind of the crucial. Maybe I'll stop soon, but I want to leave. But this is kind of the main idea. So this is the kind of really striking thing about this story is that H has a square root. And in particular, then in particular, to find this has all sorts of kind of amazing implications then for your system. That if H is actually a perfect square, it's telling you that in some sense, instead of worrying about this Hamiltonian operator, which is a second order differential operator often, you really should worry about this operator, which is a first order differential operator often. So you really, when this happens, it really kind of completely changes the nature of the problem you're working with. And there's all sorts of new structure and all sorts of new things you can do because you've taken the square root of a because the Hamiltonian has a square root. And in some sense, so in some sense, what's happening also is a way of thinking about it is that, I mean, this guy by definition is the thing which generates time translations. So you've in some sense figured out, you've in some sense decided that I found a way to take a square root of a time translation. But these things, now you have to watch out. This guy, lies in a nice Lie algebra. He's a nice Lie algebra element. This guy is mixing. This guy is mixing bosonic and fermionic. So remember that things like this are now in a Lie superalgebra. So this guy is an element of a Lie algebra, and he's got all these nice properties because of that. But he actually has a square root, and that square root, you can think of as being these guys as being generators of a Lie superalgebra. So going to superalgebras and going, what you're doing is you're now mixing together the bosonic and fermionic stuff and generalizing your notion of Lie algebra to Lie superalgebra is going to give you all sorts of interesting extra structure. So let me, let me mostly stop here, but then, so there's only kind of a couple of other things in this in this particular chapter, which I'll start with next time, you can actually you can actually make this problem a little bit more interesting. You can actually add something called a kind of a superpotential. You can take an arbitrary function of q and you can deform this problem into another soluble problem. And I'll say a little bit about that next time. But and then what we'll go on later to what we're going to go on. What I want to go on next time is then to explain how you can also think of the what's happening if you go back to get away from just a simple oscillator problem like this and go back to your single particle theory, to your free particle theory. That if you add certain kind of fermionic degrees of freedom to your free particle theory, and then you can arrange for this to happen. You can arrange for your Hamiltonian to be a perfect square, and the thing that it's the square root of is going to be the Dirac operator. So that's going to be Dirac operator here. And then maybe just to say a couple last words about. So this notion of supersymmetry. So I mean that's actually. I think there is this beautiful mathematical story about here, which is about the square root of time translations. I mean, supersymmetries have gotten a lot of attention among particle physicists in the past. And what people are when they're talking about supersymmetric quantum field theories, what they're generally talking about is a more complicated version of this, where you find a Lie superalgebra such that not only do time translations, not only are time translations squares of other operators, but also spatial translations. So you take the whole, algebra of spatial translations and rotations, and you add fermionic degrees of freedom so that not only does time have a square root, time translation have a square root, but also spatial translation also has a square root, and you get a very interesting set of quantum field theories, which maybe I'll say a little bit at some point later, and which there was a lot of hope that those had something to do with the real world, but so far there's no evidence that particular construction has anything to do with the real world. However, this, as we'll see next time, I mean, this idea, the idea that time translations have a square root, and that square root is given in some sense by the Dirac operator, is the answer to that. That actually does have a lot of real known physics to it, and we'll talk about that next time. Okay, so I guess we'll stop for today here. But any questions about this guy? I mean, this guy is a really nice little thing to play with. This is a very simple-minded kind of little calculation, which you should be able to just to see how it works. And the variant of it I'll do next time with a deforming with a potential. It's not that much trickier. So. But any other questions? Okay, well, if not, then I'll cut this off. But again, I'm here for quite a while, and do come back and talk if you want to talk about this or anything else in a minute. Okay. Okay. Bye for now then.
Thanks. Thank you.
Bye.